Hello again. Welcome to the 8th and last part of Introduction to Programming by Adrien Yudusar. So in the previous videos, we talked about all these topics and now we have just two left. So we have just Introduction to Time and Space Computational Complexity, and we talk about the big O notation, and then we gently discuss where do we go from here, having learned these basic concepts. So starting quickly, what is space and time complexity? So the time complexity is simply how much time the algorithm takes to complete the task. So how long does it take from the start to finish? And the space now is about how much memory or RAM does the algorithm consumes to complete the task. So when we study the time and space complexity of an algorithm, then we can judge if it's a good algorithm. We can judge how efficient it is, and we can compare it against alternative algorithms. Now, to give you a little background about why we care about time and space complexity. So imagine Alice and Bob were writing an algorithm to solve the same problem, and they both produce working algorithms, but which are written in different ways. And now it's time to decide which algorithm is better, so that they can integrate it into the applications. How do they actually compare the algorithms? So one idea could be, okay, let's run both algorithms at the same time and see which one finishes first. And a couple problems that could come with this idea is if the input sizes are too small, with modern computers pretty much or both the algorithms might finish instantly, and you will not be able to tell the difference really. And on the contrary, if the input sizes are large enough, the both algorithms might never finish and you will not be able to compare them. But I think the biggest issue is if you run the two algorithms, the results you get will be heavily dependent on the hardware you use. So if you're using a faster CPU, then an algorithm which was supposed to be slow might appear to be faster than the other one. You might also say, okay, let's compare them in terms of memory consumption. And just to give you an idea of what is memory consumption we are talking about here, suppose you wanted to count how many times the word hero has appeared in a book. And one approach which consumes much memory would be to say, okay, I'm going to store the whole book in memory, and then I will just try to count how many heroes are in by reading from memory. But a better approach would be you don't actually need to store the whole book in memory. Instead, you can read sentence by sentence, and at a time you only need to remember a sentence, or even you can take it further and only remember a word which you are currently reading, and just read as you go and don't consume as much memory as the previous approach. So this is something you could do. You could say, okay, let's run these two memories and use some special tools to check which one consumes less memory. But measuring memory accurately might be not so easy, not too easy, unless you really know what you're doing and you have a proper tools. And also, if there is no significant difference in memory consumption, again, you might not be able to tell the difference. And another big issue is if the problem we are working on is complex enough, then we might actually not have computers powerful enough to test the limits of our algorithms. So most laptops really have less than 32 gigabytes of RAM. I mean, that's a very powerful laptop if you have one. But generally speaking, they tend to be less than 64. Yeah. Now that raises the need for something, and that takes us to what is called the big O notation. So there is a need for this notation, and the need is we need a universal standard approach to measure the efficiency of algorithms. We need something that all programmers can agree on, and in such a way that if I send you a code or an algorithm, then just by looking at it, or if I just tell you some information in a certain way, then you will be able to know even before you run the code, you can be able to know whether this code is going to be fast or slow. So that's the need. We need an approach to measure the complexity of algorithms, and the approach has to be independent from the hardware on which we run the algorithm. Now, having that in mind, one opinion is you realize that when the input sizes are very small, we may actually not be too concerned with the complexity because any algorithm might finish in a decent amount of time. But when the input sizes become very large, that's actually when we need to worry because some might just take forever to finish the task. So, how about having a formula which can tell us how an algorithm behaves as an input size grows? Because that's the only situation in which we are most interested in. And so the solution to this problem is simply a mathematical function which happens to be called O of something. And if you know in math, we tend to say like f of x. Here we have O of something, and that will be expressed in terms of n basically, where n will be representing the size of inputs. So without further hesitation, we have what is called three tiers. So think of this as the three possible case scenarios we can have. And we have these three standard systems, and the first one is the best case, and it's called the big omega. So imagine the idea of the best case is, for example, suppose you had an algorithm which looks for maybe the largest element in an array of numbers, a list of numbers. So if you had that problem, the best case scenario would be where you are given an array which is just empty, which has nothing because you don't need to do any work. So that's the best case scenario, and that's what big omega tells you. Now big theta gives you the average case. So you have the best case, you have all the case, you have the worst case. If you put everything together and find the average, that's what big theta is all about. And now big O tells you about the worst case. And the worst case really is quite interesting. It tells us how the algorithm scales up in the worst case scenario. Like in the previous example, imagine, okay, for example, this is a good example. Imagine you had like to walk across a board, and it's probably going to be a little complicated, but imagine if you had to walk across a board and you can only, the paths you can take are limited. No, this is probably very difficult. Let's just imagine if you had a list of the previous question, you had a list of numbers and you ask you to find the this is good. You have a list of numbers and you're asked to count how many times a number x has appeared. And the worst case would be where, okay, everything in the list is the number x, I guess, something like that. But that doesn't cut it very well. Yeah, or simply let's say you have a really huge size of inputs. That could also show it. Yeah, so it's the worst case basically. And need to close this. Yeah, and now oftentimes we are only interested in studying the worst case. And why is this the case? Why are we so interested in the worst case, not the best case or the average case? Wouldn't it make more sense to go with the average case because it covers kind of both ends? Turns out it's not the case, and the reason is well explained with this story. So imagine you were going to cross a river on feet, and you want to know whether you will make it to the end alive, and by alive I mean you will not sink. So this is the information you could have. Information number one would be given by big omega, and as we saw, our good friend big omega tells us about the best case scenario. So because your only concern is at what point am I likely to sink in this river, so big omega will tell you like the least deep point in this river is only 0.5 meter deep, and that would sound cool because many people are taller than 0.5 meter. And big theta being the average case, it would give you something like this. The river you're about to cross is 1.2 meter on average. That sounds impressive, maybe not so impressive if you are careful enough. I mean, at this point, I would really ask you an interesting question. Would you really take the risk of crossing this river on feet if you had this information? You know, the average and the best case? Yeah, probably not. I wouldn't, because Big O is hiding some crucial information. Big O would give you something like, okay, in this river, actually the deepest point is 6 meters deep, and I've never seen anyone who is this tall. So most likely you would sink. Turns out this is actually why we need Big O more than Big Omega and Big Theta, because it gives us the crucial information what of what how our algorithm behaves in its worst case, in the case where it's most likely to fail. And if we design it in such a way that it can survive the worst case, then we know for sure that it will be a reliable algorithm to use in our application. We know that it's scalable. So that's why we care much about the worst case, and hence the big O notation. Now these are some common varieties of big O notation, which I'm going to discuss in details in the next slides. But as you can see, we have the big O of 1, we have the big O of log n, and we have the big O of n, and we have the big O of n square and n cube, and we have the big O of n power something power n. So what is this all about? So when you observe these graphs carefully, I guess I will change my pen. So for erase this messed up. Yeah, okay, I guess it's decided to remain there. Okay, yeah, that's good a little bit. Okay, this we do. So when you look at these graphs, on the x-axis we have the data inputs, on the y-axis we have the time. So we are studying how much time is required as the size of inputs increase. And with that, on the big O, you will notice that the time is quite constant on O of 1 somehow, and log n it's increasing, but the rate of increasing is decreasing, so the curve is flattening. On O of n it's increasing linearly, n squared the curve is shooting up, n keep shooting up even faster, n power n even more crazier. So what is this all about? So the O of 1, aka the constant time, it means that no matter the size of inputs, the time required by the algorithm will always be pretty much the same. And what this means is, just a second. Yeah, okay. So the amount of the time required by the algorithm will never change regardless of how much inputs we have. And I have a very classic example here. I trust you have probably been reading it. So this function finds the middle of a list. We find the element in the middle of the list. And what we need to do actually to find that element is we just need the left and the right of the list, and then we simply divide by 2 and find the element at that index. Turns out we can get the right side of the list by simply finding its length, which is a constant time operation in Python, because of the way elements of a list are stored in memory one after another. So finding the length of a list is as easy as checking the position of the last one on the top of the list. And then once we know the length of the list, we can simply divide by 2, and that will give us the middle element. Yeah. Then we can simply, in constant time, find the element at that position and return it. So these operations does not depend at all on the length of the list. Whether it has 10 elements or 1 billion elements, this function is expected to run in about the same time. So that's why it's called constant time, and that's why you see on the graph on O of 1 the time is constant even when the inputs are increasing, and that's usually a very desirable time complexity. And the same goes for space. If you are storing things in memory, in maybe using a couple variables which you are not building up anything whose size depends on the size of inputs, then your space complexity will also be O of 1. The same concepts apply for time and for space. So when I talk about time, also reuse the same concept for space complexity. Now the second complexity is log n. Now what's log n? Oftentimes we use the logarithm in base 2, and basically what that means is as the inputs goes up exponentially, the time required goes up just linearly. So to put that in context, imagine if it took 1 second to compute 10 elements, then it would only take 2 seconds to compute 100 elements, and so on. It would then take 3 seconds to compute, I don't know. Yeah, this is basically how it works. And the most classic example of this algorithm, of this time complexity, is a revolutionary algorithm called the binary search. And actually on this channel I have a whole video explaining how the binary search works, so check around and learn about it. But basically what we do is we are trying to search whether a given target element exists in a sorted list of numbers. And what we do is, rather than searching across the entire array of numbers, instead we check the middle, the element in the middle. We check whether it's equal, less than, or greater than the number we are looking at, and we decide accordingly. If it's equal, then we have found it already. If it's less than the number we want, since we have a sorted list, then we know that the answer we want can never be on the left of the middle element. Let me say this again. So we have a sorted list of numbers. We check the number in the middle. If that number is less than the number we want, then we know the answer can never be on the left of the middle element. I hope that makes sense. And so what we do is we will abandon that entire half of the inputs, because we know the answer cannot be there. In the same way, if the middle element is way bigger than the number we want, we know the answer can only be on the left, because everything after the middle element is even bigger than the middle element. Yeah. So to understand how it works, simply take a paper, write a list of 10 numbers which are sorted from the smallest to the largest, and then imagine if I asked you to search for any of those numbers. How would you go about searching it? Do you need to look through the whole list, or you can just suspect which path it's likely to be on? Yeah. And so the idea is you keep splitting the inputs into halves, and in the end it will take you logarithmic time. If you have 10 elements, you only need to do 3 operations to get the answer, as opposed to 10 of going through everything. And this is the actual algorithm. So we set 2 pointers, one on the left of the list, one on the right, and then we'll be moving them. So before, as long as they still haven't crossed, what we will do is we find the middle element. And in Python we can find the middle element by simply taking the left plus right over 2. But in other languages which has integers that can overflow, you better use this approach to avoid integer overflowing for like very huge numbers. But this will work in Python. So then once we have the middle element, we check whether it's equal to the target, and if that's the case, we are very lucky and we can return the middle element, because it's the desired position. It's the desired position of the target element. If that's not the case, then there are 2 possibilities. Either the middle element is smaller than the target, which is the case I have here. If that's the case, then I will move my left pointer or boundary, I will move it to one element past the mid number, because I know the answer can never be on the side which is on the left of the mid number. And then if that's not the case, then at this point that means my mid number is bigger than the target, and then I will move my right boundary to mid minus 1. If they cross each other and I haven't returned any answer, it means simply there is no answer in the list. So that's how binary search. Again, I have a whole video about it on this channel. And that's how logarithmic time comes about, because rather than going through all the inputs, we are splitting the inputs into half every time. So if we have like 10 elements, we end up doing like just 3 operations to find whether a number exists or not. And then the third time complexity is called O of n, or linear time. So this is basically going through all the inputs. So it means if n increase, then O of n increase as well. Yeah. And the good example would be in the previous example. Imagine now we just decided to go through all the number, and if we meet a number which is equal to the target, we return I. This is O of n because we saw big O is about the worst case. So in the worst case, I don't find the number, so I reach the end of the whole list without finding the number, and that will take me n time, because I have to go through n elements, where n is the number of inputs data. Now the fourth time complexity is called quadratic time. Now this usually is, suppose I gave you a list and I asked you to check if we have any two numbers which sum to a target number. So what you would do is you could grab one number and look through all the remaining numbers to see if there is any number which can be added to my first number to make the target number. So I grab a num1, and for that num1 I will look for every num2 in the array, and if num1 plus num2 give me the target, I will return them, otherwise I return not found. So the reason why this become n square is we are doing n operations n times. So for every number in the array, we are again comparing it with every other number in the array. So if we had 3 elements in the array, we will do 9 comparisons. That's why it's n square. And in coding, in your daily life programming, you will find it as a nested for loop. We have one for loop inside another for loop. And with that in mind, we can go deeper and do n cube, which will be 3 nested loops. For example, you wanted to find 3 numbers in a list that sums to a target, and you can take this as far as you want. You can make n power 4, n power 5, up to n power some c large constant number. It all groups into what is known as polynomial time complexity. Now, that being the case, now there is a second category which is called exponential time. Now exponential time, I'm going to give an example here of 2 power n. So how does this arise? If you remember, when we talked about logarithmic time, we say that the time grows linearly as the size of inputs grows exponentially. Now try to think of what the reverse could be. Try to think of a situation where as the inputs grows just linearly, then the time grows exponentially. Now, so here I have an example here. I have this binary tree, and I want you to imagine if I wanted to figure out how many paths can I take from the top to the bottom of this binary tree. For the beginning, let's imagine that we only had one level. I think I'm going to need to draw here. Let's imagine that we only had this much. Now, if we only had this much, if we only had just one level, what could we have? And my pen is behaving quite weird, but I will figure out what's wrong with it. Yeah. If we had just one level, and we wanted to figure out how many paths can we take from the top to the bottom, definitely it's just two possible routes. Now think of n as the number of levels we have in this binary tree. So if n is 1, we have two possible routes we can take. But if n becomes 2, if we have 2 levels, now the number of possible routes we can take become 4. Now we can see it. And interestingly, if n becomes 3, the number of routes we can take all of a sudden becomes what? 8. Because I can come all this way 1, 2, 3, 4, and it's the same on the left side. So you realize that as n increases by 1, the number of routes required is doubling. And that's what 2 power n is all about. At every stage we are creating 2 possible paths to take. Yeah. So you might imagine that if next time if there was another layer, it would become what? It would become 16. Yeah. And that's 2 power n. Now 3 power n would be like we have 3 paths coming out of every node. Yeah. And this is what is called exponential time complexity. And for space it's the same. Now the last and usually the slowest and the most avoided time complexity, whenever possible by the way, is something called the factorial time. Now the factorial time is not seen too often, but one of the most famous situation where we have the factorial time complexity is if we want things that require us to generate or find all permutations of something. So for example, imagine I had this list of numbers 1, 2, 3, and I wanted to figure out how many ways can I rearrange these 3 numbers. How many possible permutations can I have of 1, 2, 3? And it turns out mathematically we can find factorial of 3 by I guess 3 times 2 times 1, and that gives us 6. So we expect to find 6 possible permutations of these numbers, and that's what we have here. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Yeah. So these are the possible permutations, and you can see how huge this can get. If for example the list had like 10 numbers, you could really already be dealing with very huge outputs, and hence the time. So this is probably the slowest time complexity in space as well, because you see if you are generating this 2-dimensional array, you need to be building it up as you go. So in the end, the time and space complexity you need would both be factorial time, O of n factorial. And here we have a quick summary. Remember that O of 1 is the constant time, doesn't change regardless of the inputs. Log n, very fast. The time required increase linearly as the inputs increase exponentially. And we just go through everything, and it scales up linearly to the size of inputs. Now I didn't talk about n log n, but as you can see, it's n multiplied by log n. So you have one operation which takes log n, but you are doing it n times. For example, if I had that list and I was asked to find 2 numbers which sums to x, I could say, okay, I will grab one number and I will binary search for its complement. If the target is 8 and I reach 2, I can quickly binary search for a 6. If I find a 6, then I have 2 numbers which sums to 8. So because I'm doing binary search n times, then it becomes n log n. This complexity is very common in sorting algorithms, like the quicksort, merge sort. Yeah. And then we have n square, and we have the exponential time complexity, and we have the factorial time complexity. So you can see how these values, you can see how they shoot up really fast as the inputs just begins to increase. So as a take-home point, it's always desirable to have at least polynomial time complexity. So whenever possible, you can try to stay away from exponential time complexity and definitely factorial. Whenever possible, log n if possible, n if possible, and log n. Starting to become a little bit heavy, but still okay. N square, maybe it could be improved to n log n if you are careful enough. N cube, check whether you really need to be doing all that work. And if it can't be avoided, just go with what the best you can get, the optimal solution. And now we're at the second part of this course. Usually the programming courses don't go this far, but I just thought I could talk about some possible career paths you can take in programming. And I don't mean to say that by what you have learned in this course you are prepared for these paths. I just mean to show you, to give you, just to throw out some ideas of what you might expect to come across with, so that you don't have to spend weeks searching just to know what is there. At least you can go straight into what you want, because trust me, in my situation I spent so many weeks searching just to know what is there. Okay, so we have three categories of programmers. We have the career developers, and those are the ones who work for companies and get a regular paycheck. Now we also have freelancers. Now the freelancers, they work for their own and they don't owe any allegiance whatsoever to any company. Instead, they get hired to do a task, they finish it, they get paid, and they move on. And then we have the interprogrammers. So these are the programmers who build products and then build businesses around them. Now, some of the common path, there is web development, which is really huge now, because many things are moving to the web now. I'm one of the people who are really optimistic with the web. And when we talk about the web, there is front-end web development and there is back-end. And so front-end web development, you basically need to be familiar with HTML, CSS, which are markup and styling languages, and JavaScript to build the user interfaces of web applications. And then if you are interested in the backend of web development, what you'll be doing is mainly building what are called APIs, application programming interfaces. And APIs are consumed by the front-end application, and what they do, you can think of them as messengers standing between the front-end and the database, passing back and forth data in form of JSON or something else, and handling some necessary business logics. And by the way, for backend developers, they have so many options. You can, these days it's really popular to use Python for the backend with some frameworks like Django or Flask or a few other, but Django is the biggest one, and Flask. You could also use other languages. You could use JavaScript as well for the backend with Node.js. You could use things like you could use Java. You could use .NET, you could use the old PHP, you could use Ruby on Rails, which is also becoming a little bit of a niche today, but many things are still running on it. Same story for PHP. You really have a ton of options. Personally, I like Python, and I also like JavaScript. And then you could become the so-called full stack web developer. And easily put, this is someone who knows something about everything. So they can alone put together a working website. Let's leave it here. They know something about front end and back end, enough to have a website up and running without hiring any extra person to work on the front end or the back end. Now there's also another area called DevOps, which involves mainly handling infrastructures. So we build the application and now we need to deploy it. The developers might be able to deploy it, but when they the applications become very big, or maybe we are in a huge company, then we really need people to specialize on managing infrastructure, because now it's extremely important. So the DevOps guys are often working on this. And then we have mobile app development, which is obviously have two divisions: the Android development, which now has like the a larger market share globally compared to iOS, and which is all about iPhones. And until now, Android developers had been working in Java for a long time. I mean, you could also use other languages to build mobile apps, but the Java is just more suitable for it. But recently, Google has announced Kotlin as the primary language of Android development. So if you are new to Android development, check out Kotlin. And but Java is still used as well. And also for iOS, the same story. They used to code a lot in a language called Objective C, but now Apple has introduced a language called Swift, which is supposed to be easier to use than Objective C, and you can use it to build uh, Apple products basically. Yeah. And then, but now I also have to mention that these days there is a very hot wave or a trend towards cross-platform mobile development, because this is expensive. You see, if you are maybe a startup business, you might not have enough capital to hire two separate teams, one team to work on Android development and a team to work on iOS development. Instead, if you could find a solution which can allow you to hire one team which writes one code base that can run on both Android and iOS platform, that would save you a lot of money, and it would be very desirable to the business. So that's why these days we have frameworks for cross-platform mobile app development. You hear a lot React Native, which is being supported by Facebook, and it's basically a JavaScript framework that uses another framework called React. And there is also Flutter, which is developed by Google, and it uses a language called Dart. And these two are like the biggest we have, but there's a ton of tools which are emerging in the market now, and many people argue that this could be the future of mobile development. So check out if you are interested. Now we also have other areas like desktop app development. Some people say that this market is dying today, but I would disagree, because I'm recording this on a desktop. Many of you will be watching this on a desktop, and we are using desktop apps really. And you might think like there are not many startups today shipping or selling desktop applications, but there is still a ton of companies which have to maintain their existing desktop application, and they have to keep releasing new versions. So there is always going to be a need for desktop app developers. So again, we have Windows, macOS, and Linux. For Windows people, they really like to use a language called C Sharp, because it's backed by Microsoft and definitely somehow made for developing desktop applications for Windows. And for macOS, again, you will use Swift, and for Linux, you can use pretty much anything. And then we have embedded systems. You can think of printers, ATM machines, all those things which have programs running, interacting with their low-level systems. And I believe they use C++ a lot, and Java. And then we have data science, which is very, very hot today. I think was ranked as the hottest career for a couple years in law. And here Python simply rocks. If you're interested in data science, you really have to run Python. There is another language which is used in data science called R, but today Python is just rocking. Yeah, there's also big data engineering. Check it out if you're interested. And then there's machine learning. Originally, I personally believe it should be included in data science, but yeah, I said let me add it. Yeah. So machine learning, again, Python is leading, because the two biggest machine learning frameworks we have are TensorFlow, which is backed by Google, and PyTorch, which is backed by Facebook. Now, TensorFlow is more popular with businesses and individuals who might not be that much tech savvy. You still need to be tech savvy to do machine learning, definitely. But PyTorch, according to one professor whom I took a machine learning class from, is they like it more in academic institutions because they can kind of, I don't know, maybe reverse engineer stuffs. But TensorFlow is a little bit more, it's made to be user friendly, and that comes at the cost of much abstraction. So most of the code is not exposed for the sake of making life easy, definitely for users. Yeah, but the whole point is those two frameworks are built in Python, and so many tools which are used in machine learning are written in Python. So it's definitely what you want to be doing if you're interested in machine learning. And then we have enterprise tools, and this is one place where Java has really been reading for a long time, and it's probably still reading and might remain reading in a while. So we are talking about big companies, banks, government institutions, and we are talking about the tools they use internally, whether it's desktop application or websites, just the tools they use for their internal operations. So if you are interested in this market, you may want to check out Java because they have so many many applications written in Java already. And then we have the cloud development or architecture, which is new and rapidly growing. Really interesting to look into these days. So basically, you have these days companies are no longer hosting their applications in their local servers. It's no longer cool to buy a server and keep it in your house or your office place and host your application there and your database there. What is cool today is to leverage the infrastructures from big companies like Google or Amazon or Microsoft, and then deploy your application on their actual infrastructures, and also take advantage of so many tools they offer in the cloud, things like Kubernetes, things like managed database, which have all the cool features. Yeah, so the cloud development is really interesting to look into in 2020 and going forward, because it's new and there are not so many people who are skilled in these tools. So the biggest players we have now are Amazon Web Service, Google Cloud Platform, Microsoft Azure, and we also have other smaller players like DigitalOcean, and yeah, there are so many of them. So definitely do check it out if you are interested in catching up on a new and trending market. And then we have testing automation, and this is basically automating the testings for application to make sure that any change which we made passes the tests, and so that we know that the code will always work. It will not fail during the night when we are sleeping and the users are using it. And then we have database administration and database management. Now the area of database was growing a little bit silent lately, but since the era of machine learning took hit, now it's back again, because now all of a sudden now the fight in the machine learning industry has turned toward database. And the reason for this is, now when I was doing machine learning course in my university, we realized that many of the algorithms we could actually download them from the internet. They are publicly available. You could download some algorithm, you could download models for doing this or that, translating languages, doing this, doing this. The code is publicly available. You can download the code and use it yourself. The challenge is to get enough data to train it to be accurate enough. That's where now the fight in machine learning is. And that's why all of a sudden database is, again, it has never been this important, but now it's even more important. Yeah, so these are the guys working with uh, securing, managing databases, making sure everything is smooth, making sure data is not lost, optimizing queries. They write so many SQL. By the way, SQL is a query language which is used in relational databases like MySQL or PostgreSQL or others. And then we have the NoSQL databases like MongoDB, which uses documents to store data and everything. Yeah. And then we have the cybersecurity I'm not very skilled in this industry, but I think the penetration testing and ethical hacking, these are the people who basically with authorization and with who are certified to do this work. They might attempt to hack a system or an application, and if you see any vulnerabilities, rather than exploiting it, you just let the company know, and they will go ahead and fix it or hire you to fix it if that's what you do. Yeah. And then we have competitive programming. These are the people who we can say who do programming as a sport. Let's say it like this. So they solve problems, they write algorithms, and they compete and earn rewards. So they're just as there are football competitions, there are also programming competitions. Yeah, and they oftentimes use platforms like Code Forces, which I believe is probably Russian, Topcoder, AtCoder, Hackerrank, ReadCode, etc. There's so many of them. So if you're interested in this, check out some of these platforms and go ahead and start practicing and then compete. I believe you can get a couple competitions every week if you sign up on several platforms. And then we have technical management positions, or these engineers. They form teams, and you definitely need managers. And as a manager of a technical team, you in most cases you will be required to have some background in programming yourself. So this might help you if this is what you intend to be at. And we have more and more and more. So, as a homework for this week, search about some of these fields that you are interested in now that we are at the end of our class, and then use any job listing platform to find out which ones have more openings in your region. Then I added this hesitantly but ran about freelancing and just know what it's about, and who knows, you might be interested in doing it. Yeah, just it's an option which is good to be aware of. And then some final tips as we conclude the course. First, if you're interested in web development, check out this thing. Check out Free Code Camp, very organized, really platform, which is free by the way, and it's big in the industry and it's recognized. You can run web development, you can do projects, you build sites, and they guide you through it, and you get certificates when you complete the task. So this is something I wish I didn't know in my early days of running web development. And also check out Traverse Media. I've been following this guy for a while. Now I know I can trust him. He's a very honest man, and he don't try to sell you bad stuffs. He just give free content, and he's a very good man. His brand and his channel is called Traverse Media, so check it out. He's all about web development. And then I really encourage you to do something called project-based running. So rather than just running to code randomly, I encourage you to do this. Pick a project that you wish to work on, start working on it, and then do what all the programmers does. So Google what you don't know and run it. So that's basically what every programmer is doing around the world. Working on things, we meet what we don't know, you search it, you read on some Stack Overflow posts, and then you run, you read some documentation, and you figure it out and you keep going. You meet a second issue, you search about it, you solve it, you keep going. That's basically what every programmer is doing. I have not come across of any programmer who builds applications offline, if I should say so. We always have some Chrome tabs on the side, Googling. Yeah, and then practice, and then build some stuffs regularly. And the last one, just remember that every frustration you encounter is reducing competition in the market. Because whenever you meet a difficulty and you are very frustrated, which I know to be the case because I have experienced it myself, just remember that if you get past this, then you really will shine more in the market, because this is the point where many people give up surgery. So when you encounter this frustration, just imagine that getting above this difficulty is going to make me more likely to get opportunities in the market. So see it as an opportunity rather than being overly frustrated or having stress and anxiety. Yeah, coding can be challenging, and it's really challenging, and that's why many people don't do it. Yeah, but if you set your mindset properly, you will like it, and it's a very, very rewarding career, and we saw so many opportunities. So this week we saw about the computational complexity, and then we discussed some paths from here onward. And finally, this is where I congratulate you for making it to the end of this course. It's been quite some time, it's been a long time running. I have intended to make this video short, but certainly I haven't been able to. I really congratulate you for staying on and watching all the way up to the end. Let me know if via my email or the comment section if you have enjoyed this course, and if you really like this course and you will help like it, I would really appreciate if you send me a simple email which simply lets me know how you took this course and what you liked about it, what you didn't like it, what you think I could improve in the future if I make other courses. Yeah, and I would be really grateful for that. So thank you so much for following this video to the end, and I really wish you the best of luck, and I hope to see you somewhere on some programmers platform. And yeah, just send me a hi when you see me there. Okay, thank you so much. I will see you in the future, and all the best.